Here we have a flash drum problem where the pressure of the flash drum is given, but not the temperature. And so what this means is we're going to have to also incorporate an energy balance into solving this problem. So I'm going to go through the energy balance and mass balance setup before we actually solve the problem. But we have a feed coming in that is entirely liquid, and what we have is an optional heater, and this feed is coming in at a high temperature and pressure, and then we have a throttling valve that reduces the pressure to give us our two phases, and then the separation of the two phases in the vapor and the liquid. What we are given the temperature of the feed, but we are not given the temperature of the flash drum. And so because we have evaporation going on, we are going to have a change in temperature. The temperature of our flash drum is going to be lower than the temperature of our feed, and so what we will have to do is we'll have to use an energy balance to calculate the temperature of the flash drum and then solve the equilibrium relationships and material balances for the vapor and liquid phase flows and components. We are given the pressure. All right, so we are given the pressure, but we will need to find the temperature of the drum. So we usually assume that the flash drum is well insulated, or we also say it's adiabatic, so we can neglect any heat loss from the drum itself. The valve that I mentioned here that is prior to the flash drum is a throttling valve, and so the delta H across this valve is 0. And then if we are assuming that this is operating in steady state, the energy balance becomes the feed flow rate times the enthalpy of the flow rate is equal to the output, which is the vapor flow rate times the enthalpy of the vapor plus the liquid flow rate times the enthalpy of the liquid. For these problems, we're also going to assume that we have ideal solutions and ideal gases, and so this means that Raoult's law is valid. And so what that means is that the fugacity coefficient is equal to 1 and the activity coefficient is equal to 1. And this is usually valid for flash drums when we're dealing with somewhat well-behaved components, because we're usually dealing with lower pressures. And as long as we have components that do not have strong intermolecular interactions, then we are okay with the ideal liquids as well. This also means that we don't have to worry about enthalpies of mixing. And so this simplifies things quite a bit. And so what this means is that we can calculate, well, we could look at these enthalpies up, but since we do not know what our mole fractions are going to be in the outlet streams, we can do the calculations to calculate these enthalpies fairly readily. And so for the enthalpy of the inlet stream of the feed, that will be a function of the mole fraction times the heat capacity of the liquid. And in here we are going to assume that the reference temperature for each of these streams that we're dealing with is the same, and so those will cancel out. Now the heat capacity of the liquid, that's usually can be assumed to be a constant. So that's a fairly easy calculation as long as we can look that up. For the liquid stream, of course, that's going to be the mole fraction times the heat capacity of the liquid times the temperature. And so again, if we can look that up, we can figure that out. Note that this is going to be the temperature of the drum though, and we do not know that going in. So we cannot just, this is going to be part of the solution process. And then for the vapor stream, of course, that's going to be the mole fraction times the heat capacity times the delta T, where this, again, this is going to be the temperature of the drum. Note that we are going to include the delta H of vaporization. We have to include the delta H of vaporization because we are going from a liquid to a vapor, and so that is something that we will have to incorporate into our energy balance. So our overall energy balance, what we do is we just substitute each one of these terms into this overall energy balance, and that will give us our final energy balance equation. Now, moving on to a problem. So this problem is taken from a textbook written by Phil Wankat at Purdue. It was published in 1988. So it's been around a long time. This is a flash drum where the temperature of the drum is not known. So we're told that the feed on a mole basis is 51.7% propane, 9.1% pentane, and 39.2% octane. We're told that the feed temperature before it goes through the throttling valve is 95 degrees C. The flash drum operates at 250 kilopascals. And we are asked to find the temperature of the drum, the vapor and liquid flow rates, the mole fractions of the components in both the vapor and liquid streams. And then we are also told to assume that Raoult's law is valid. So we have the ideal gases, ideal liquids, don't have to worry about delta H of mixing. So just thinking about this, a preliminary observation is that propane's more volatile than the pentane and octane, and so what we get out of the vapor should be enriched for propane. What we get out in the liquid stream should be enriched for the pentane and the octane. Another thing to note is that if this is going to be at high pressure, if the feed stream is going to be at completely liquid, that upstream of the throttling valve is going to be a high pressure, and so we can calculate what that minimum pressure is below. So first thing we need to do is start assembling the given information. And so again, I am going to use the indexes of 0, 1, and 2 because that's how MathCAD does things for my components. So I enter my feed, I enter my feed composition, my feed temperature, I know what the flash drum is, and just to check to make sure everything is entered correctly. Since Raoult's law is valid, I'm just going to insert this into here. The partial pressure is equal to the mole fraction times the total pressure in the gas phase. The activity coefficients are 1, and our equilibrium relationship is given here by Raoult's law. We can also define the relative volatility, and for Raoult's law that reduces to Psat for each component divided by the total pressure. So the first thing that I'm going to do here is start assembling our material properties. And we are going to have to get Psat information. We are also going to have to get heat capacity information. So getting our Psat information, there's a number of sources you can use. I am using NIST webbook for these. And so I've given you the web page that you can look at. So I've got these here for propane, pentane, and octane. And one of the things that I want to check when I get done is to make sure that these temperature ranges are valid. And it looks like going into this that these temperature ranges are going to be fine. The other thing to remember is to make sure that you're careful with the units that are used in these Antoine equations. Temperature is in Kelvin. A lot of times they're given in Celsius, so make sure you're careful about that. And the pressure is going to be in bar, and then we are dealing with a log base 10 calculation, so again make sure that you are careful with your calculations there. So if we would like, we could calculate a Psat, but again we do not know what the flash drum temperature is, so it really doesn't do us much good at this moment. Next thing that we need heat capacity information for the vapor phase. And so for that, I went to my Smith and Van Ness textbook. Table C1 in the appendices gives us the ideal gas heat capacities for each of these components. And so it goes propane, pentane, and octane for each one of these components. Again, you need to make sure that you are careful with entering the information with the tables when they use scaling factors, and also be careful with the units that are used. We're using absolute temperature. Another material property we're going to need is the heat capacity of the liquid phase. And note that our heat capacity in the vapor phase is going to be dependent on temperature, and so this is going to be the temperature in the flash drum that we will use. For heat capacities in the liquid phase, we can assume that those are pretty constant, and especially with respect to everything else that's going on inside our flash drum. And so we can look those up. Again, I looked those up in the NIST webbook. So this is the heat capacities of the components in the liquid phase, and then I also looked up the delta H of vaporization for each of these components. And again, they're can be assumed to be relatively constant. You will look those up and make sure that you are at least within the temperature range of interest. What's that range? Well, we will go back and check and make sure. Now, the first thing that we can do is we can get an estimate of what the flash drum temperature is by doing a bubble point and dew point temperature calculation at the flash drum's operating pressure. We know that that temperature, to be able to separate into two phases that liquid stream, that temperature has to be between the bubble point and dew point temperature at that operating pressure. And so to get that, we need to do those calculations. And so in doing that, we need to rearrange our Antoine equation. And so I've got that here, and I've just copied my given information there. So I'm going to bring over our bubble point temperature calculation. This is something that you'll find in your thermodynamics textbook. And we can solve this using a solve block in MathCAD. We do not need to use an iterative programmatic approach to that. And so we are going to set our liquid phase concentrations to the feed concentrations that are coming in. We're going to do a first initial guess of our temperature and our vapor phase concentrations. And so I'm going to, a way to do that is just to do a weighted calculation of the Tsat at our operating pressure. And so our initial guess is going to be 332 Kelvin, and our initial guess for our vapor phase concentrations, I'm just going to set that equal to the feed concentrations coming in. And so we can set up a solve block. We have unknowns are the temperature and the Y composition, so that is 4 unknowns, and so we're going to need 4 equations. And so we have our overall pressure, equilibrium relationship, and then our mole fractions. Here I have the Y0, Y1, and then I use the equation that the mole fractions have to sum up to 1. Use a MathCAD command to find the values of the bubble point temperature. We get a value of 273 Kelvin, so about 0 degrees C, pretty cold. And then you can see we have our compositions for the first bubble that is formed, and you can see that it's highly enriched for our lightest component, which is propane. You can see that the mole fractions, calculated mole fractions of the pentane and heptane are quite low. So that makes sense. Next thing we need to do is a dew point temperature calculation, and so I'm going to bring this over in block. Again, go to your thermodynamics textbook to get all these equations. And we are not going to use an iterative programming approach. We're going to use the simultaneous equation solvers that we have in MathCAD. So for a dew point temperature, given P and Y, we need to have an initial guess of, given P and Y, we want to calculate T and X. So we're going to set our our values of Y, and then we are going to do a guess of T. And so what I said was I'm going to guess that our initial T is going to be the temperature of the heaviest component. And so that was 434.8 Kelvin, and then my initial guess, let's see, I don't believe that is going to be necessary. That is extra. So we want to calculate X. So again, we have 4 unknowns, temperature and the X compositions, and then we want to calculate the pressure. We want to give our four equations. So our 4 equations are the pressure relation, equilibrium relation, and then for each of the mole fractions, go through and tell MathCAD to do the solution, and we get a value of about 400 Kelvin. Note that this is much higher, and also note that that first little droplet of liquid that is going to form is going to be highly enriched for the heaviest component, the octane in our case. And so what we can find from this is that our initial flash drum temperature should be between the bubble point and dew point pressure. So somewhere between 399 or about 400 Kelvin and 273 Kelvin. And so a convenient initial guess when we do our flash drum calculations is to just take the arithmetic average of those. If we wanted to, we could add some kind of weighting, but that's not necessary. Another thing that I was kind of interested in solving this problem was what is the pressure upstream of that throttling valve? We were only told that it's 95 degrees C and it must be 100% liquid. So what should that pressure be? And so we can figure out that pressure by doing a bubble point pressure calculation where the X values, the liquid mole fractions, are equal to our feed, and then we can go ahead and solve for that bubble point pressure in composition. And so what this tells us is that the bubble point pressure at those conditions, at that temperature and concentrations, is going to be 21.8 bar. And so what that means is that upstream of our throttling valve in our system, so up here, our pressure needs to be at least 21.8 bar to maintain a liquid. And we are told that the pressure is 2.5 bar, so it's almost about a tenfold, about a 9 to 10-fold difference in or decrease in pressure as we go to our into our flash drum. So that was not part of the solution, but the formal solution, but I wanted to see what that was. So now what we can do is we can start to actually solve this big system of equations. And so we're going to use MathCAD solve block so that we can avoid having to do iterative calculations. Remember, for Raoult's law, we can define the relative volatility in terms of the ratio between the saturation pressure and the total pressure. And then we should realize that we have 9 unknowns in our system. We've got 3 unknowns for the liquid phase compositions, 3 unknowns for the vapor phase concentrations. We do not know our outlet liquid and vapor flow rates, so that's 2 unknowns. We also have T of the drum. The temperature of the flash drum is an unknown. And so what we're going to do is we're going to enter initial guesses for all of these variables, all of these unknowns. And so I'm going to keep things simple and just say we have 1 mole. We're just we could put it mole per hour, kilomoles per hour, whatever you want, but I'm just going to use a basis, a feed of 1 mole. And I'm going to guess that we have about 0.2 moles of vapor, and so that means that there should be 0.8 moles of vapor in our initial guess. My T drum, remember we calculated that above as the average of our dew point and bubble point temperature. And then I just entered some values, just making sure that they summed up for 1. I'm assuming that in the vapor phase it's going to be highly enriched for the propane, and in the liquid phase it's going to be highly enriched for the heaviest component, the octane. So now I need to generate all of the equations that we have. And so there's a lot of equations here. I'm going to bring them all over at once. We have our given statement command in MathCAD, and then the first equation that we have that I've written here is the Rachford-Rice equation. And remember, the Rachford-Rice equation is our combination of material balance and equilibrium relationships. And so this is our Rachford-Rice equation. We're using this because it converges very nicely and is pretty stable. This is our overall material balance, and this is our species material balances. And so this is for the liquid phase mole fractions, and instead of writing 1 for the third component, I just said that the sum of the mole fractions has to equal 1 in each of these in each of these liquid and vapor streams. And so these you can find from your thermodynamics textbook or from any of your equilibrium stage ops textbooks. Then we have our energy balance. So the energy balance, all I did was I took that initial energy balance that we looked at and I substituted in for the enthalpies. And since we were using the same reference temperature for all of these, the reference temperature cancels out, and so we get this term here, or we get these terms here. And so this is our inlet energy coming into the flash drum. This is the enthalpy, I should say, of our vapor stream. And so that takes into account the heat capacity of our vapor plus the delta H of vaporization for each of our components. And that is going to depend on the total enthalpy is going to depend on the mole fraction times. So basically how much of each of those components vaporize. And then of course our liquid stream. So now what we have, remember we had 9 unknowns. We have 8 equations for our material and species balances in equilibrium, and then we have our energy balance equation. So we have 9 independent equations. We can then tell MathCAD to solve for all of these unknowns, and so we use the find command in the simultaneous equation solver. And so what you see here is we have I'll put this over here, we have the temperature of the drum is calculated at 341.88 degrees Kelvin, or about 342 Kelvin. Is that in between our dew point and our bubble point? Yes, it's in between our dew point and bubble point. Our liquid flow rate and our vapor flow rates are given. Remember, this is a 1 mole basis. So about 44% of our stream goes into the liquid phase, about 56% goes into the vapor phase, and then we can see our distribution of the components. You see in the vapor phase, we expected it to be highly enriched for the propane, the lightest component, and it was. We have a very small amount of our heavier components coming out in the vapor. Our liquid phase, we would expect it to be not to see much propane in it, and that is the case. We would expect our liquid phase to be highly enriched for the less volatile phases. So those are our answers. We can also check our answers pretty well, pretty easily in MathCAD. So again, here I've got our feed conditions, our drum temperature that we calculated, just making sure that is in between our dew point and bubble point temperature. As I went over before, it looks like we're good there. We can do our material balance. So our overall material balance information, here's our feed coming in, our liquid and our vapor streams. You could do the math by visual inspection, or you could actually check, and you can see that everything checks. Everything is positive numbers. We don't see any abnormalities like negative mole fractions or negative liquid or vapor flow rates, so that's good. What about our energy balance? We can look at our energy balance terms and make sure those things add up and make sense. And so our total enthalpy coming in, 65.09 kilojoules, and then our vapor stream leaving is 29.8. Our liquid stream leaving is 35.29. If you don't want to do the math in your head, you can do it here in MathCAD, and you see that these enthalpies match up. So that gives us more confidence. And then as far as looking at the phase equilibrium, does the phase equilibrium add up? Remember, our pressure of the flash drum was 2.5 bar, and so we can calculate what the total pressure should be given these assumptions, and that indeed is the case. Our pressure of our flash drum is equal to what we calculate by phase equilibrium. So that is doing the solution when we have to solve for our energy balance as well. We're given the temperature of the feed, but we are not given the temperature of what the temperature is in the flash drum. We have to incorporate, remember, we have to incorporate the two phases and also the phase change in those calculations. A lot of the flash calculations that you'll do in your thermodynamics and stage ops courses will actually give you the temperature and pressure of the flash drum. But these problems illustrate what happens if we do not know that temperature going into the problem.